Good evening. Tonight what we are going to be talking about is matter. And the big question is, what is matter? Well, matter is anything that has mass and volume. As we've already learned during class, mass is how much stuff an object has. So the more stuff something has, the more mass it has. The less stuff something has, the less mass it has. As far as volume is the amount of space that something occupies. So the more space it takes up, the more volume it has. The less space it takes up, the less volume it has. So your question is what is matter then? Well, some examples of our matter, which both has mass and volume, would be pens. They would be air. And some people can be like, hey, I don't think air has mass. Well, it actually does. It's just very low mass, okay, proportionally to its size. And then there's other things like paper. Anything that's tangible that you can actually touch is definitely going to be matter. So then you question yourself, well, what is not matter, since it seems like so much is matter? Well, you've got light. You have sound. You have heat, gravity, microwaves. And what all these are missing are both the volume component and the mass component of the definition of what is matter. In this class, we're going to be measuring a lot, and we need to be able to be consistent with other scientists in what they measure. So what we use in this class, along with every other science class that you've ever taken, is the metric system. This is also known as SI units, which is the International System of Units. So internationally, all scientists use these base units, okay, to measure substances. So what are the base units? Well, it depends on what you're measuring to see what unit you'd use. So if you're measuring length, you'd use meters, which is abbreviated as M. For volume, you'd use liters, which is abbreviated as L, and it typically is written with a capital L, not a lowercase l. And grams would be to solve for a mass or measure a mass, which would be abbreviated as G. All of this should be reviewed to you at this point in your lives. Okay. In addition, in order to make the units, the base units, either larger or smaller, they use prefixes based on the power of 10. So we've got deca, hecto, kilo, deci, centi, milli. And all of these either are larger or smaller than our base units of meters. So for example, I'm going to do kilo. So this one would say, I need 1,000 of my base units. So I'm going to say, let's say, grams. So I'm going to need 1,000 grams for every 1 kilogram. So I need a lot of little grams to make up one big kilogram. That's the 1,000 to 1 ratio. So for every 1,000 of my base units, such as grams, meters, or liters, I get 1 kilogram, 1 kiloliter, 1 kilometer. Okay? It's the exact opposite for this. Okay, and the bottom. These all are larger units than your base unit. These are all smaller units than your base unit. So we'll go with centi, since that's a very commonly used one. In this case, it is saying that I need 1 meter in order to get 1 meter. So this is your base unit, is always the first one on this particular notes sheet. One of my base units for every 100 of my prefixed units. So for 1 meter, I need 100 centimeters. Okay, because a centimeter is a lot smaller, in fact, 100-fold smaller than 1 meter. So I need 100 centimeters in order to make up 1 meter. So that statement would be for every 1 meter, I need 100 centimeters. Or for every 100 centimeters, I need 1 meter. Okay, so let's do some example problems. And how you do this in this class, we are going to be using proportions all the time. So if I know that there's 1,000 grams for every 1 kilogram, I need to calculate the number of grams in 35 kilograms. So the importance is that you partner up the correct things. So I know that for every 1,000 grams, I need 1 kilogram. Okay, or if I have 1,000 grams, I have an equivalent to 1 kilogram. That I know is proportionally going to be the same as if I had 35 kilograms, how many grams? Whenever you are setting up a proportion, it is extremely important that whatever you are solving for, doesn't matter whether it goes on the top or bottom, but you need to make sure that your units align. So if I am at grams on the top, I need to be at grams on the top on my proportion. If I am at kilograms on the bottom, then I need to be kilograms on the bottom of my other side of my proportion. So now I'm ready to fill in my numbers. So it says calculate the number of grams. So I'm trying to figure out grams in 35 kilograms. Okay, so I'm going to put 35 kilograms. And I know that proportionally it's going to be the same as 1,000 grams to 1 kilogram. So now all you need to do is cross multiply and solve for x. And when you do solve for x, you get 35,000 grams. So to do the second problem, I know that this for every statement gives me, and it doesn't matter if I write the 100 centimeters on top or on the bottom. I'm going to just write on top because it's first. 100 centimeters. Okay, sorry, that's a little hard to see. Change it up for every 1 meter. So this is a true relationship. I know proportionally that is going to equal, and even before I fill in any numbers, I'm going to put my centimeters on top up here and my meters on the bottom because I know my units have to align. So centimeters on top on the left, so it has to be on top on the right. So I need to figure out, calculate the number of meters, so I do not know meters, in 245 centimeters. So just like the last problem, all I'm going to do is cross multiply, okay? And when you solve for this, you get 2.45 meters. All right, now we are ready to talk about the law of conservation of mass, which was an extremely important part of the lab that you just completed. And what that lab stated is that all particles of matter or mass can either be rearranged, but neither created nor destroyed. So if basically what that's saying is if I start with 12 grams, then the only thing that I can end with, even if it looks different, I can only end with 12 grams. I can't have more, I can't have less. So it would end up with 12 grams. So no matter what, I can't go up or down. Okay? Matter can change what it looks like, it can change its shape, size, but the mass you start with is the mass that you end with. This is a true statement. This is what chemistry is based primarily off of. So now it's important to draw, it asks you to draw a before and after particle picture that represents this. So I'm going to draw a solid, okay, and here are my lovely little particles. They are closely together, which means that they are a solid because they are right next to each other. They maintain their same shape and size. And then what I'm going to do is I'm going to have a gas floating around. Okay, these are shown that they are different particles, not only because they are different colors, but they are also in different states of matter because the gases are spread more apart, and they are also in X versus a circle. So it's just very obvious to anybody who's looking at that these represent different particles. So what I'm going to show is that somehow they're going to combine and change it up. So I'm going to end up with, let's say, a solid still. But now these particles are going to be attached. And if you look at it, I know that my mass was conserved because I started with 3 X's in the beginning, and I ended with 3 X's, or 3 of those particles, and I started with 9 particles of the circles, and I ended with 9 particles. So therefore, my number of particles, or my amount of stuff, stayed the same before as after. All right, I hope you had a great time learning about matter, and enjoy the rest of your evening.